This week we will study VC dimension. VC dimension is very interesting concept to understand the learning complexity for infinite hypothesis class. So in the previous weeks we have studied pack running and no free lunch theorem. So what was pack running? So when the hypothesis set H is a finite set, epsilon delta packed learning is possible with this amount of samples. We show this. So here epsilon and delta indicate we can guarantee at most epsilon test error with probability 1 minus delta. Then we say our algorithm is packed learnable with parameter epsilon and delta. And essentially from theoretical analysis, we know that the sample complexity is low bounded by 1 over epsilon times log times the cardinality of hypothesis set H plus log 1 over delta. But the question from the previous course lectures was, what if we have infinitely many hypotheses? From the no free lunch theorem and this bound, what we learn is essentially when the number of hypothesis element or functions grows up, our complexity also grows up, and especially when the number of hypotheses becomes infinity, then the sample complexity also go to infinity, and from the no free lunch theorem, there are always some counterexample our algorithm doesn't work, right? But today we will discuss a little bit different story. Infinite classes can still be learnable. Of course, not always. So we should define some complexity measure of hypothesis set, not just number of hypotheses in your hypothesis set, but there is something else. Okay, this is VC dimension. So let's review a simple example in our textbook, which is example 6.1. So let H be the set of threshold functions over the real line, namely the hypothesis set consists of all function H that discriminate the input domain, the real line input domain, to 0 or 1 using only one single threshold A. So when you have this real line, you pick the threshold A, and all this area having value 0, and all this area having value 1. Okay, and since A is also a real number, we can define infinitely many different hypotheses. But when you consider only this HA function, only this thresholding function, indeed the function looks like very simple, right? We do not consider any linear function. We do not consider any polynomial function. We do not consider any more exponential function or log function. We just consider very, very simple thresholding function. So we can expect, we can expect that this simple function will require very tiny amount of training samples to learn true hypothesis, if the true hypothesis belong to the class. If the true function also make the output 0 or 1, based on just a simple hypothesis with true ground truth, the threshold A star. Okay, then we just need to learn A star, and that is much more simpler than before. So that is lemma 6.1. Let H be the class of threshold as defined earlier. Then H is a packed runnable using the ERM rule, empirical risk minimization rule, with this amount of samples. We can learn with this amount of samples. Okay? Recall that what was no free run theorem. In the no free run theorem, one condition was that when we don't know any information on true hypothesis, then we cannot learn with infinite many hypotheses. But in this case, we know what is true hypothesis. N is the shape. We know the true hypothesis having some threshold function with ground truth threshold A star. Of course, we don't know what is A star at the beginning, but N is from this simple shape and from this information, the truth function follow very simple generation rule. We can learn something that is lemma 6.1, and the proof also very simple as well. Let A star be the ground truth threshold such that A star x is indicator function, whether input x less than A star or not. And of course, the test error is equal to 0 with this ground truth hypothesis function. And let A and A1 be the constants such that A0 is less than A star and A1 is bigger than A star, and the x belong to A0 A star and x belong to A0 A star and A1 is equal to epsilon, the probability for the data generation distribution. And if there is no such A0 and A1, let's just use minus infinity and infinity. And we also define B0 and B1 such that the max x having 1, the operable 1 among your training samples, and B1 is max x among your training sample having output variable 0 among your training sample. And if B0 is minus epsilon and B1 is minus infinity, B1 is infinity if there is no such instances. This is 5 condition. Then a sufficient condition for the test error is smaller than or equal to epsilon is that both B0 is greater than or equal to A0 and B1 is less than or equal to A1. If both are true, then we can say that we can guarantee the test error is less than or equal to epsilon, because when B0 is greater than or epsilon, A0 and B1 is less than or A1, then we can at least guarantee that the ERM rule will have 0 error with any threshold A in between B0 and B1, and B0 is bigger than A0, and B1 is less than or equal to A1, and we know that there is A star, and this interval probability is epsilon, and essentially either this or this is max possible error area, and this area is less than or equal to epsilon, so we can say that the test error is less than or equal to epsilon when both are true. B0 is greater than or equal to A0 and B1 is less than or equal to A1. Okay, when you pick any threshold in between B0 and B1, you have zero training error. But when you're threshold is outside this interval, then you always have some training instances does not match it with your threshold, right? So your ERM rule always make a threshold in between B0 and B1. And when you have this threshold, the error range is only this area, and this area probability mass always less than or equal to epsilon. Okay, so that is our key component to show lemma 6.1. And when B0 is less than A0 and B1 is greater than A1 happen, all this is happen when all example in training sample are not in this interval or not in this interval. And we know that this interval probability mass is epsilon, and this interval probability mass also epsilon as well. So using the independent property of training sample generation process, with this amount of sample, we can say that this event will occur with probability delta over 2. This event will occur with probability m-os delta over 2 with this amount of sample, which comes from this inequality sign.